Good morning, class, and welcome to lesson 5.2.1. Objective: I will be able to convert between exponential and logarithmic equations. Today's lesson will review a very important function family, the logarithmic family, commonly called log. Both exponential and logarithmic functions are widely used to model situations in biology, chemistry, business, economics, and engineering. Logarithms are useful when dealing with very large values. Logarithms, the word is derived from logical arithmetic, were developed in the late 16th century by the Scottish mathematician John Napier. By shortening the process of computation, logarithms served for many years to speed up the work of navigators, astronomers, and engineers. Leoma has hooked up two function machines as shown in the diagram at right. Part A. When Leoma puts 4 in the first function, 81 comes out. Then 81 goes in the second function. What comes out? Well, if you're taking 3 to the x and you're plugging in 4 and 81 comes out, then the log base 3 is really asking 3 to what power, question mark, equals 81. That value has to be 4. These functions are inverses of each other. One will undo the other. Next, Leoma puts 2 into the first function machine. What number comes out? Well, if you take 3 squared, 9 is going to come out. Then what comes out of the second function? Well, it undoes 3 squared. It's really asking, again, 3 to what power is equal to 9? And that happens to be 2. If x goes in the first machine, then what comes out of the second machine? Well, if you plug x into the first machine, 3x comes out of the first machine, and then the second machine will undo that, and x will come out. How are the functions that are inside the function machine related? We just talked about that. They are inverses. Now for part E, suppose machines are reversed. If y goes into the log base 3 of x machine, and then a comes out, write this as an equation. Well, the log base 3 of y has to equal a. If a goes into the 3x machine, what comes out? Write this as an equation. So 3, a goes in, and then y comes out. So how are the answers to D and E related? Well, by the definition of logs. If we have the log base 3 of y equaling a, then the inverse 3 raised to the a has to equal y. So you may recall that a logarithm, called a log for short, represents the power to which a fixed number must be raised to produce a given number. Key piece. It's the power to which a base must be raised to produce some number that we are given. For example, log base 2 of 16 equals 4 because 2 to the 4th equals 16. Just a note as we work these next problems, a common logarithm is a logarithm with base 10. It is expressed as log base 10 of x. But because we use it so often, we usually just write the log of x. So anytime you see the log of x, we're really talking about log base 10 of x. So now without a calculator, evaluate each of the following logarithmic expressions. Look for and record any patterns or interesting results. Now in order to work these, let's keep in mind that base b of x equaling some constant is the same as b to some value has to equal x. These are inverses of each other, and we can use one to help solve the other. So in part A, my base is 3. So I'm going to write it as its inverse. Excuse me, log base 3 of 9. In order to evaluate that, that means I'm going to take that base of 3. I'm going to raise it to some exponent, and I have to get 9. Well, we know that 3 raised to the power of 2 gives us 9. So therefore, the log base 3 of 9 equals 2. Let's try E. I'm again going to use that inverse expression. If I have the log base 7 of 7 to the 5th, that means 7, this 7 right here, raised to some power has to equal 7 to the 5th power. Well, what does the exponent over here have to be in order for the two sides to be equal? That exponent has to be 5 also. Now let's try one that's a little bit harder. Let's try G. Now I'm starting with the log of base 0.2 or 2/10 raised to the 5th power. So I'm going to write 0.2 to some power has to equal 5. 0.2 is the same as 1/5 raised to some power has to equal 5. Well, that exponent has to be a negative 1. Now in H, that got cut off a little bit, so I'm just going to rewrite this. This problem is really 10 raised to the log of n. So we're actually going to start in this form. We're going to rewrite it in terms of a log. So my base is 10 here. So I'm going to write this as the log base 10, but remember I don't have to write the 10 in there, of some number has to equal the log of n. Well, what does this have to be in order to equal n? Well, it must be n. In other words, I have to take the log of n to equal the log of n. So 10 raised to the log of n is really just n. Now what I'd like you to do is pause this, try a few, and then come back and check your answers. Okay, welcome back. You can take a look at your answers up here for B and C and D. In D, just talking about that, our base is 10, so 10 to some power has to be 1. Well, that power, that exponent, has to be 0. Because anything that is 0 power gives you 1. In part F, my base is 2. So now again, I'm going to actually rewrite this expression in terms of logs. So log base 2, and that 2 here comes from this base of 2. So log base 2 of something has to equal to log base 2 of 16. That something in there has to be 16. Now as we get into the last 4, I, J, K, and L, instead of using a question mark, I'm going to start using X, just because of some mathematical operations. But we're really not finding X in this case. I'm just using it as a variable. So my log base 4 of the square root of 2 raised to the third power. Well, that's going to be 4 raised to something. We're going to call that x. Has to equal the square root of 2 raised to the power of 3. Now that 4, that's not the same as the 2 on the right. This 4 needs to be rewritten in terms of base 2. Well, 4 is 2 squared raised to the power of x. Really gives me on the left side 2 raised to the 2x. On the right side, the square root of 2, well, that's the same as 2 to the 1/2 power. Now with the power to a power, I'm going to multiply those two exponents and get 2 to the 3/2. So now this exponent over here has to equal this exponent in order for the left side to equal the right side. So that 2 to the x has to equal 3/2. Multiply both sides by 1/2. And x comes out to be 3/4. We really don't want to say x is 3/4. We want to say the log base 4 of the square root of 2 raised to the third power equals 3/4. And so now I have the log base 2 of x equaling 2 times the log base 2 of 9. There's a power property that you can learn about a little bit later, where I could pull that 2 that's out in front up as an exponent of the 9. So my left side hasn't changed, but the right side, log base 2 of 9 squared. Well, this x has to be the same as 9 squared. So x equals 81, but I really don't want to say x equals 81. What I want to do up here, say that 4 raised to the log base 2 of 9 equals 81. Now in part L, there was a little piece left off. There was an x up here. So this is really 4 raised to the log base 2 of x. Just like in part J, excuse me, just like in part J, I'm going to take that 4 and I'm going to rewrite it as 2 squared. And again, I have this power to a power, so I'm going to multiply those together. So I have 2 raised to the 2 times log base 2 of x. Now I'm going to employ this property of logarithms and rewrite this as the log base 2. This 2 goes right there, of some number has to equal my exponent up here. And again, I'm going to pull this 2 out in front up as an exponent. So now the left side, log base 2 of x, has to equal the log base 2 of x squared. Therefore, x has to equal x squared for all values where x is greater than 0. And you'll learn a little bit more about this when we get to another slide in this lesson. So my answer, 4 raised to the log base 2 of x, is really equal to x squared. So there's another useful logarithm, and it's called the natural logarithms, or logarithm base e. It's expressed as the log base e of x, but more often we write that as the ln of x. So what we're really saying is that the log base e of x is the same as the ln of x. This is just like when we write the log base 10 of x really is the same as the log of x. Over here, we just don't write the base 10. Over here, we rewrite it as the ln of x. So without a calculator, evaluate each of the following. In part A, this is really saying the log base e of 1. That's another way to think about it. We want to figure out what that equals. We'll use our definition of logs. E is my base. So E to some power has to equal 1. And anything to the 0 power gives us 1. So my exponent has to be 0. Now what I'd like you to do is pause this, try B, C, and D, and then come back and check your answers. Okay, welcome back. You can see the answers are written here for you. And in part B, we have the ln of E. And so that another way to write that would be log base E of E. And using our definition of logs, E to some power has to equal E. Well, that has to be a 1. Part C, I skipped writing it out in terms of log base E. I just know that the ln, the square root of E, my base in this situation is E. So I'm going to take E to some power and it has to equal the square root of E. Well, what does this exponent have to be? Well, the square root of E is the same as E to the 1/2. So I get 1/2 for my exponent. Therefore, the ln of E, the ln of the square root of E is equal to 1/2. And in the last one, my base is E. So I'm going to write this as log base E of something has to equal this exponent, ln of x. Rewriting this in terms of ln, this is the ln of something has to equal the ln of x. Therefore, we get x. Another way to think about this is base E and the ln, they undo each other. Well, if they undo each other, what are you left with? X. 5-54. Can a logarithm have any base? Can you take the logarithm of any number with your team and investigate the possible values of n, m, and b in this equation below? Remember, in this equation below, the inverse of this equation is b raised to the m is to equal n. So what I've done is chosen some values for n. Let's say n takes on maybe a -2, 0, and a +2. And for b, we're going to choose the same values. Let b be a -2, 0, and a +2. So what happens if you pair n being a -2 with b being a -2? Well, you have the log base -2 of a -2. And if you were to type this into your calculator, go ahead, pause this, type this into the calculator using the change of base, which can be found underneath the math button, you'll get a non-real answer. In other words, sometimes it's going to work and sometimes it won't. So if we apply the definition of logs, my base is a -2, so -2 to the m equals -2. Yes, m actually does work for this one. M could be 1. But if I take the log of the log of a negative base of some negative number, is that always going to work? And the answer is no, it's not. And again, if you want to pause this and give it a try, let n be a -4 and b be a -5. You're not going to be able to take the log of that either. Now, what about if n is a -2 and b is 0? So the log base 0 of a -2. Again, if you go to your calculator and type that in, it's not going to work. Another way to look at it is 0 to what power is going to give you a -2? Well, there's nothing that will ever work because 0 times itself will always be 0. And what about the log base 2 of a -2? Can a positive number be raised to a power and give you a negative output? Again, That's not going to work either, because a positive number times a positive number will always be positive. It cannot equal a negative 2. If you want to take a look at all of these and think through them, very rarely can n and b just be any numbers. There has to be a unique relationship between the two. What does work is if we go all the way down to the bottom. Log base 2 of 2. 2 to some power equals 2. Yes, m is going to equal 1. And if you were to take the log base of any positive number of another positive number, you're always going to be able to calculate that value. Therefore, here's what we can conclude when we start examining log base b of n equaling m. B has to be a positive number. It has to be greater than 0. N also has to be a positive number. It has to be greater than 0. But m can be any real number. So keep that in mind as we work to simplify logarithms. So now in 41, they want us to try to solve the following equations. So let's employ our definition. Just as a reminder, log base b of n equals m means b to the power of m has to equal n. So in part A, ln means my base is e. So e raised to the first power has to equal 3/2 x plus 9. Now solve for x. Subtract 9 from both sides. And then multiply by 2/3. So x equals e minus 9 times 2/3. Take a minute to solve b and then come back to this video. So pause it and I'll have an answer for you in just a minute. All right, welcome back. Now log of a negative 3 equals x. Remember, the base in this problem happens to be 10. So we take 10 raised to the x has to equal a negative 3. Well, 10 is a positive base, and x represents the number of times you're multiplying that base together. And so a positive number times a positive number can never equal a negative 3. Therefore, there's no solution. So just to recap a few things. Describe the relationship between logarithmic expressions and equivalent exponential expressions. Again, that is the log base b of n equaling m. Its inverse is b to the m equaling n, where b has to be greater than 0 and n has to be greater than 0. Using this property, I'd like you to evaluate the following. Pause this, come back, and check your answers. Okay, welcome back. Oh, here are your answers. You can take a look at that first row. Pretty straightforward. Your base is always b, so b to some power has to equal b. Well, that has to be 1. Here, b to some power has to equal b to the a. Well, that exponent has to be a. And b to some power has to equal 1. Well, anything to the 0 power equals 1. In the second row, I'm going to use that exponent portion of the log inverse, and the log base b of something has to equal the log base b of a. Well, this has to be a. Remember, this is log base 10, so 10 to some power has to equal 10. Again, that exponent is 1. And the last one, you're going to have to use your calculator. 10, because that's my base, to some power has to equal e. A little trial and error. 10, your exponent has to be 0.4343. Here's some math notes that just talk about the relationship between exponents and logarithms. Please take a quick read of what's on this page. And again, note what's happening at the bottom, talking about what b can be and x. Please complete the homework and the exit slips. The exit slips may not seem like they're that important. It may seem like extra work, but the problems that we put in the exit slips do tie into the lesson, as well as what you're going to be able to be seeing on the tests in Chapter 5. Wishing you all the best. Have yourself a great day, and look for a video on 5.2.2 in the next day or two.